Hi everyone, thanks for watching this recorded presentation. Lustre, as part of high-performance computing infrastructures and data centers, now has to face growing legal requirements about data security. Among them, the need for end-to-end and at-rest encryption is drawing more and more attention. Now, this presentation is going to show how we are able to address this requirement for encryption by implementing encryption directly at the Lustre client level. That is to say, by handling all encryption and decryption work on Lustre client side. So, here is the outline for today. First, a reminder about what is encryption for Lustre. Then, I will give details about encryption features in Lustre 2.14. And finally, I'll explain the remaining work regarding encryption. So let's get started. What is encryption for Lustre? The use case we want to address is to provide a special directory for each user to safely store sensitive files. So the goal is to protect data in transit between clients and servers, but also to protect data at rest. The solution proposal relies on the FSCrypt kernel API. The current users of this API are ext4, F2FS, and UBFS file system. And the core principle is that pages in the page cache are always representing clear text data. For the user space part, we want to rely on the FSCrypt user space tool so that we can tell which directories we want to encrypt and how. What do we have in 2.14 release? We are providing the ability to encrypt file content, which means we encrypt on write and we decrypt on read. And we also provide the ability to set encryption policies on directories. So it means we support new IO control commands that are sent from user space. And we are also able to handle encryption context atomically. In 2.14, we do not have support for file name encryption. So here you have a list of all the patches that have been merged in 2.14 in order to be able to support file content encryption. There are 22 patches listed here. Client encryption implementation is compatible with many different I/O patterns that we are used to with regular files. For instance, on encrypted files, we are able to support holes. So it means that when you have a hole in a file, we will not replace it with zeros that are then encrypted and stored on disk. We will keep the holes. But of course, it means that the existence and location of holes is not hidden. We do support truncate on encrypted files, whatever the size at which we truncate. So it means that in some cases we need to read the page that is going to be truncated, decrypt it, do the actual truncate, then re-encrypt and rewrite on server side. We are also able to support mmap on encrypted files. This is possible because, as I said earlier, with FSCrypt, all pages in the page cache are clear text pages, so mmap is working naturally. We are able to support direct I/O as well, which is interesting. For instance, ext4 doesn't support direct I/O for encrypted files. We do, because we're able to twist the pages being used for sending in RPCs and use those pages to proceed to direct I/O and encrypt or decrypt content. A direct consequence of this feature is that we are able to support file mirroring, because file mirroring works thanks to direct I/O at the moment. We're also able to support data on MDT, And we have extensively tested the use of 64K page size clients with encrypted files, so it works. And for instance, you can write a file on a 64K page size client and then read back the same file from a 4K page size client. So how do we handle encryption context? Encryption context is very important because this is the information that stores for each file the information about the way this file is encrypted. This encryption context is stored in an extended attribute, and hopefully this information is not changed after file creation. So with Lustre, we guarantee encryption context atomicity. In the setting case, it means that we send the encryption context to the MDT along with the create RPC. So it closes the insecure window between creation and setting of the encryption context, and it also saves a set XRTTR request, so it's both important for consistency and performance. The getting case is addressed as well, so we have made modifications in the code so that servers would return the encryption context upon granted lock reply. So it deals with all the requests like lookup, get ATTR, open, truncate, layout. So this makes the encryption context retrieval atomic, and it also saves get XATTR request again to improve performance. Now let's talk about how to decide on which directories to encrypt. Lustre needs to support new I/O controls provided by FSCrypt. Version 2 of the FSCrypt API gives the ability to revoke pages from the page cache when encryption key is removed. The thing is, this version of the FSCrypt API landed in Linux 5.4, but on Lustre client side, we need to support CentOS 8 and Ubuntu 18. So the solution retained was to copy the FSCrypt code from the Linux kernel into the Lustre tree. We renamed it to LLCrypt in order to avoid name conflicts, and now it's available in the libcfs module. So once that was done, we wired up the new I/O controls in Lite. Lustre supports these new I/O controls, but concretely, how to tell which directories to encrypt and how? Well, thanks to the FSCrypt user space tool. It works with Lustre out of the box, thanks to the FSCrypt API support from the kernel. And the good thing is that it supports encryption policies v2. Here I have listed the main FSCrypt commands, but I propose to go for a demo to illustrate how it works. Okay, so here we have a user named user0, which is part of group user0. We are running on a Ubuntu 18 release, kernel 4.15. So let's mount Lustre 2.14 that is installed on this node. As you can see from the mount options, encrypt is implicit. So let's create a dedicated directory for user0, grant him access rights, so that without privileges, this user can create normal directories and create normal files. We are here to do encryption, so let's configure encryption with FSCrypt. So first you have a command that configures FSCrypt globally. If we look at the configuration file, we can see that the policy for content and file name as well, but in 2.14 this will be ignored. Very important, we have policy version 2, which means that files will be removed from the page cache when keys are removed. So now let's set up Lustre with FScript, and let's create a specific directory that we name Vault, and let's encrypt this directory. So this is done as a regular user. We choose to use a custom passphrase. We have to name the protector that we want to use in order to protect this Vault directory. We input a password, and then we're good to go. It means that every content in this directory is going to be encrypted. So we can write files, we can create subdirectories. Those directories will inherit the encryption policy. Of course, we can create encrypted files in that subdirectory. We can read the files that we just created. We can list, of course, directory content. Now we decide to lock the directory, so this is going to remove the key and also remove the pages from the page cache. So now if we try to read a file, it doesn't work, and it says that the required key is not available. We cannot write to the file. If we list the directory content, this is allowed, but we see the content because in 2.14 names are not encrypted. Now let's unlock this directory, input the password, and we regained access to the Vault directory. We can read files, we can write files as well. So in fact, FScript doesn't give direct access to master keys. Instead, it handles protectors, and those protectors are wrapping the master keys. So the good thing is that thanks to that mechanism, we can change a protector's password. So here we can see that we have the shield protector that is defined for our Lustre file system, and we are going to change the password for this protector. So we specify the protector, we input the old passphrase, then the new passphrase, and this is done. Here, file content is not re-encrypted. We have just changed the password of the protector. So now let's lock again this directory and leverage another mechanism offered by FScript, which is the ability to use multiple protectors for the same directory. So here we have a different user named other user, and this user is part of the same group. So first, let's create a protector for this other user. We use a passphrase, we name the protector armor, and okay, now that this protector has been created, let's get back to user 0 and let's share this encrypted directory among the group. So we grant access rights, and now we are going to add a new protector to an existing policy. So basically it means that we have a policy that protects a given directory, and we are going to specify that we want a second protector, so this newly created protector, to be used for this policy. So we specify the policy that is given by the status command. Of course, this has to be done by the two users. This is not something that can be done without agreement of any of the parties. So each user has to input his own password in this procedure, and when it is done, we have two protectors for the same policy. So now let's get back to other user and let's try to unlock the vault directory. Other user has its own protector named Armor, so let's unlock the vault directory with this protector. It's unlocked. Now we can see that we can list the directory content, and of course we can access the files. For instance, we can read the files. Now let's talk about performance. Here you have a description of the testbed used to run IOR benchmarks. We are interested in file per process, sequential I/O, in order to measure bandwidth performance. In right, as you can see from this graph with Lustre 2.14, the orange bar shows a performance drop of around 30%. In read, we observe a performance drop of around 20%. To investigate those results, we made some modifications in the way client encryption is implemented in order to test various hypotheses. The first hypothesis we tested consists in using in-place encryption with FSCrypt. Remember that Lustre normally uses bounce pages because the pages in the page cache must keep clear text data. So by using in-place encryption, we save bounce page allocation. Actually, it breaks encryption-decryption capabilities, but IOR does not care. The other hypothesis we tested is called void encrypt here, and it consists in hacking the FSCrypt primitive so that it does not actually encrypt data, but it still handles all the rest, including the bounce page allocation. So from the graph, if you compare the two gray bars, you can see that with the no bounce code, we have a performance drop of around 10% only, and with the void encrypt code, we have around 30% performance drop. So it shows that it is really bounce page allocation that hurts performance when we do encryption. So the next move is to leverage Lustre enc pool mechanism, initially developed for Kerberos encryption, so that bounce pages for client-side encryption are taken from this pool instead of being allocated for every call to the FSCrypt primitives. Now let's talk about future work, that is to say encryption of file and directory names. We have just started a POC tracked under LU 13717. Basically, it consists in wiring LLcrypt API up in Lite to encrypt and decrypt names. We have to convert from plaintext to ciphertext names before sending requests to the MDT, and conversely, we have to convert from ciphertext to plaintext upon server replies. We have two cases to support. When we access with the keys, of course, we have to present actual names and carry out decryption and encryption conversely. And we also have to support the case of accessing the file system without the key. And in this case, we need to base 64 encode the ciphertext names. This access without the key is required because we have to support a number of syscalls without the key. For instance, we need to be able to list the directories and their entries without the key. We must be able to read file metadata with stat, for instance, and without the key, it is also possible to remove files and directories. So, supporting name encryption is a challenge in Lustre because when the name is encrypted, it's no longer a valid path name, not even a well-formed string. So we could not just simply base64 encode the encrypted names because every encoding mechanism doesn't have a 100% efficiency. So consider that we have an encrypted name that is name max long. If we encode that, it will exceed this system limit, so it would not be a valid name. So we really need to support binary names. Hopefully LDiskFS and ZFS backend file system are capable of handling binary names. So it means that the clients are going to send binary names to servers, and the servers would need to be able to handle those binary names. So what about preliminary testing of this POC for name encryption? Surprisingly enough, it works fine with DNE, but in fact it's not really a surprise because thanks to feed mapping, there is no particular aspect to take care of. Unfortunately, in this POC, feed to path is broken because path is built on server side, and our implementation is made so that a Lustre server side is not encryption aware. And of course, we would have to run metadata performance benchmarks in order to see what's the performance penalty when we have file name encryption. So to conclude, a few words about release compatibility. Lustre 2.14 has content encryption only. Future versions, 2.15 or 2.16, will have name encryption support. But the thing is, the FSCrypt policies are designed to handle both content and name encryption. So consider the case where you create a new file system with 2.14. You create files, you activate encryption, so those files will have their content encrypted, but not their names. And then imagine that later on, you upgrade to a release that is capable of doing file name encryption. Then in this case, this new version of the Lustre code would try to decrypt names that are actually not encrypted. So we need to tell Lustre that some files have only their content and not their names encrypted. So we have created a Lustre-specific encryption mode that is called LLCrypt mode null, and it is enforced in Lustre 2.14, which means that whatever the encryption policy you specify for file names, it will be ignored by Lustre and replaced inside the policy with this null encryption mode. So the projected roadmap is as following. In 2.14 that will be released, we are providing content encryption, FSCrypt inclusion, and encryption policy support. And later, hopefully in Lustre 2.15, we'll provide metadata encryption and performance optimizations. That's all for this presentation. Thanks for watching. Shall you have any questions, please reach out to me now or later. Thank you.